And welcome back. We are now moving on to section 9.2 on matrix multiplication and various properties. Matrix multiplication and some properties of multiplication. So addition and subtraction and scalar multiplication, which we did in section 9.1, were relatively straightforward. Matrix multiplication is a little more complicated. So let me first illustrate it via an example. Suppose A is the 2 by 3 matrix 1, 5, negative 3, negative 1, 4, 2. And B is the 3 by 2 matrix negative 1, 2, negative 3, 4, 2, 1. So these certainly cannot be added or subtracted because they do not have the same order. They do not have the same dimensions. However, they can be multiplied because the rule for multiplication is different. And here's the way you want to think about it. The order of A is 2 by 3, and the order of B is 3 by 2. So if I want to multiply A times B, what I like to do, or at least mentally, is put the orders of the two matrices beneath them. So beneath A, I'll kind of imagine or write 2 by 3. And beneath B, I'll write 3 by 2. If these two inner numbers are equal, like they are here, then matrix multiplication is allowed. And once we know matrix multiplication is allowed, then we're interested in the product. We're interested in the matrix that I get back, assuming that it is a matrix, because I haven't defined exactly how to multiply matrices, but it is a matrix. And its dimensions will be the dimensions of the outer two numbers. So when you multiply a 2 by 3 matrix by a 3 by 2 matrix, it's well defined, you're allowed to do it, and you get a 2 by 2 matrix result. If, on the other hand, you try to multiply the matrices in the opposite order, so B is 3 by 2 and A is 2 by 3, I see again that I am allowed to multiply them. And in this case, the product, which we'll call Q, not to confuse it with P, is actually a different matrix. It is a 3 by 3 matrix. So what we see here for the first time in your mathematical career is that when you multiply, the order makes a difference. This is not true with regular numbers. 3 times 5 and 5 times 3 are both 15. In fact, one of the basic rules of elementary mathematics, called the Commutative Law of Multiplication, is that you can multiply in either order. You don't like the order? Switch them, no problem. But with matrices, you cannot do that. With matrices, it's very important to realize that the order matters. So, we're only in section 9.2. We're going to have a bunch of sections here. As we progress through the chapter, it's very important to remember and to be aware of the fact that you cannot change the order when you're multiplying, which means anytime you multiply on the left or on the right, you have to make sure that it's in the right location. So if I have a matrix equation and I want to multiply both sides on the left or both sides on the right, no problem. But multiplying one side on the left and one side on the right, two different things, you cannot do it. So now that we have decided that you are allowed to multiply these matrices, the question is, well, what do you get when you do it? So let's do AB first. We'll do both of them just to show you. So I'm going to rewrite the matrices 1, 5, negative 3, negative 1, 4, 2. That's my A matrix. My B matrix is negative 1, 2, negative 3, 4, 2, 1. I know that the result is going to be a 2 by 2 matrix. So I am looking for 4 numbers. If it's a 2 by 2 matrix, I want 4 numbers. The top left, the top right, the bottom left, the bottom right. 1, 2, 3, and 4. Those are my 4 numbers that I want. So let's focus first on the first one. So here's how I like to do it. I ask myself, which row and which column is this number going to be in? Well, it's going to be in the first row and it's going to be in the first column, right? First row, first column. So what I do is I look at the first row of the first matrix and the first column of the second matrix. First row, first column, 1, 1. First row, first column. Now, what you notice here is that the number of elements in the first row and the number of elements in the first column are the same. There's 3 elements and 3 elements. And in fact, that's why, if you look above, that's why this is the necessary requirement for matrix multiplication to be allowed. Those two numbers have to match. The number of columns of the first matrix and the number of rows of the second matrix must be the same. In this case, they're both 3. So what I do is I multiply corresponding elements, the first by the first, the second by the second, the third by the third, and I add them together. 1 times -1, that's -1. 5 and -3, that's -15, for a total so far of -16. -3 and 2 is -6, for a total of -22. So the first entry, the top left entry, will be -22. When I go to the next entry, it's in the first row, second column. So I look at the first row and second column of my matrices. I even sometimes like to cover up the rest with my fingers. So all I see are the first row, 1, 5, -3, and the first column, 2, 4, 1. Multiply, 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 and then add them. 1 times 2 is 2, 5 times 4 is 20, for a total of 22. -3 and 1 is -3, for a total of 19. Next entry, bottom left, second row, first column. -1 times -1 is 1. 4 times -3 is -12. That makes -11. 2 times 2 is 4. Total -7. And finally, second row, second column. -1 times 2 is -2. 4 times 4 is 16, for a total of 14. 2 times 1 is 2 more, for a total of 16. So A times B is -22, 19, -7, 16. Why do we define matrix multiplication this way? Great question. We'll answer it later. For now, it's just, this is how we do it. Let's do BA just to show you what we get in the other direction. So for BA, -1, 2, -3, 4, 2, 1 times 1, 5, -3, -1, 4, 2. We know from above that we're going to get a 3 by 3 matrix. So top left entry, the first one is in row 1, column 1. Well, row 1, column 1. -1, 2 is the first row. 1, -1 is the first column. I get -1 and -2 for a total of -3. Next one, row 1, column 2. Well, row 1, column 2, -1 times 5 is -5. -5 and 8 is +3. Row 1, column 3, -1 times -3 is 3. 2 times 2 is 4, for a total of 7. Row 2, column 1, -3 and -4 is -7. Row 2, column 2, -15 and 16 is 1. Row 2, column 3, 9 and 8 is 17. Row 3, column 1, 2 minus 1 is 1. Row 3, column 2, 10 and 4 is 14. And row 3, column 3, I get -6 plus 2, I get -4. So we get two completely different matrices depending on which order we do them in. And just be aware, sometimes one direction matrix multiplication is defined and the other direction you can't even do it because the numbers don't match up properly. An example would be if A was, let's say, 3 by 2 and B was 2 by 4. AB, 3 by 2, 2 by 4, gives me a nice product, which is 3 by 4. No problem. BA, this is now 2 by 4 and 3 by 2. Don't match, not defined. So not only is it sometimes you get a different matrix depending on the order, but sometimes you can only do one direction and the other one you can't even do at all. And of course, there are situations where the order does not matter. There's special matrices out there that just happen to have the property that in either order you get the same thing. One of them we are going to spend some time on. The rest of them just think of them as coincidences. That, wow, okay, that was unexpected. It happens, it's just not expected. So given all of that, let's now do another example. This one is it's an example of matrices, but there's actually a context. It's not just random numbers. So let's do the following example. This is on page 379. It says, a diet research project consists of adults and children of both sexes. The number of participants in the survey is given by the following matrix. A equals, now the matrix is 75, 180, 110, 250. That's the matrix. And they label what the rows and columns represent. The first row represents males. The second row represents females. And the first column represents adults. And the second column represents children. So if I said, for example, how many female children were in this survey, the answer would be 250, because the female and children entry is the bottom right entry. So then it gives me a second matrix. And it says the number of daily grams of protein, fat, and carbohydrates consumed by each child and adult is given by the following matrix. This is a 2 by 3 matrix. The numbers are 15, 20, 25, 8, 16, 20. And this row is the children or child row. This row is the adult row. And this column is the protein column. This column is the fat column. And this column is the carbohydrate, or just carb column. Notice that for adults and children, in one matrix, the adults and children are given by columns. And in the other matrix, the adults and children are given by rows. And this has to do with the fact that when we multiply, remember we multiply rows, columns. We want the rows and the columns, the rows of the first matrix and the columns of the second matrix to correspond to each other. So let's read the question. A, determine AB. They just want to know what is AB. Well, I don't need the context to answer that question. I can just do the math. Now, these numbers are relatively large, and it's not impossible to do the matrix, but since my calculator can do the matrix as well, we want to have practice with both. Remember, on paper 1, it's a non-calculator based test. You'll have to know how to do these by hand. But test 2, paper 2, is a calculator based test, so you can do it by calculator. So we should learn how to do it by both. So on the TI-84 calculator, I hit second matrix, and the matrix button is the 5th button on the left. It's in blue, which is why I have to go to second mode. And it lists names, math, edit. I first want to edit because I want to create my matrices. So I'm going to edit matrix A. So I hit enter. I'm going to make this a 2 by 2 matrix, and I'm going to put in the number 75, 180, 110, and 250. Once I do that, I quit out, second quit. Now go back in there, second matrix, edit again. This time go down to matrix 2, which is a 2 by 3 matrix, and I'm going to put in 15, 20, 25, 8, 16, and 20. Again, if you're having trouble finding these, or you're a little slower, pause, rewind. That's the beauty of this. So now I'm going to second quit out of that as well. So now my 2 matrices A and B are edited and they're ready to go. Now for the third time, second matrix. This time I just hit enter by A. And what that does is it puts A on the stack. Then second matrix again. This time I scroll down to B and hit enter for B. So now I have B on the stack. Hit enter again, and it gives me the matrix. Of course, if it wasn't allowed to do this matrix, it would also tell me error. But this one gives me 25, 65, 43, 80, 54, 75, 36, 50, 6,200, 77, 50. Sometimes we will use matrices, we will use the computer to compute matrices. Sometimes we'll do it by hand. We want to have practice with both. So that is the matrix AB. Now part B says, what exactly is AB? Now the book says AB32, which is the third row, second column entry of AB. Unfortunately, there is no third row, second column entry of AB. So that's a mistake. And if you actually look at the answer, which you shouldn't do yet, but if you actually look at the answer, it doesn't give me AB32, it actually gives me AB23, which does make sense. Second row, third column entry. We know this is 7750. But they didn't just ask for what is it? They said explain the meaning of it. So what we need to do now is we need to go back into our matrices and see where it came from. How did I get 7750? Second row, third column. So that's second row of this matrix and third column of this matrix multiplied together. That's where the 7750 came from. Well, 110, 250 is a row for females, and 2520 is a row for carbohydrates. So we have 110 female adults having 25 grams of carbohydrates each. We have 25 children having 20 grams of carbohydrates each. So when we multiply, and add, we're basically getting the total grams of carbs eaten by the females. That's what the 7750 physically represents. And then for part C, it says, explain why BA does not exist. Well, B is 2 by 3, A is 2 by 2. These numbers do not match. BA, don't say equals, just BA is not defined. And if they want a little more, you say, well, because the integer numbers don't match. Their book answer is BA is not possible since the number of columns in B is not equal to the number of rows of A. So 3 and 2, those are not equal. Bam, multiplication is not defined. So now that we've defined multiplication, let me go back a page in the book and just give their boxed definition of how to multiply. It says, here's a definition. It says if A, matrix A, has dimensions m by n, and B has dimensions p by q, then the product AB is defined only if the number of columns of A is equal to the number of rows of P. In other words, if n is equal to P. And when the product does exist, the dimensions of the product is m by q. Of course, that doesn't tell me how to find the product, so we have to go back one more page even before that, where it says if P is equal to AB, then each element of P, i.e. P sub I j, the ith row, jth column entry of P, is found by summing the products of row I of A, not of row, I should products of the elements or of the corresponding elements elements of row I of A and column J of B. So that's the technical definitions, or the technical way of defining a product. But at the end of the day, if you just follow the procedure that I showed you and not worry about all these fancy words, that's how you get the product. So we want some properties now. Property number one, AB is not equal to BA necessarily. Sometimes it is coincidentally, but in general, if you have two matrices, the order matters. They're not equal to each other. However, while the commutative law, which is the switching law, does not hold, the associative law does hold. And the associative law is when you have three matrices that you want to multiply together, you have to ask yourself, do I want to first multiply the second and third and multiply those by A on the left? Or do I want to first multiply A and B and multiply that, whatever I get, by C on the right? Notice that the order of ABC does not change. These are equal to each other. It is called the associative law, and you can prove it, although we're not going to do it. You can prove that these are equal. Also, the distributive law holds. Just like it does for regular numbers, there's two versions of the distributive law. You can have the sum B plus C multiplied on the left by A, and the A distributes. Notice that the A remains on the left in both situations. Or you can have A on the right, and it also distributes, but again, in this case, A remains on the right in both cases. So those are three very important properties. Don't switch the order. That's the most important. But quite often, we're going to use the associative law or the distributive law in solving matrix equations. So, you're allowed to use those. Now, when dealing with numbers, there are two numbers that are foundationally more important than pretty much all the rest, 0 and 1. 0 has the property that if you add it to any number, you get the same number back. And 1 has the property that if you multiply a number by 1, you get the same number back. Now, we already know that any matrix plus the 0 matrix in either order, the 0 matrix being the one with all zeros. Now, I say the one with all zeros, but depending on the dimensions, there's many with all zeros. So when I write these equations, it's the one that has the same order as A, so that you are allowed to add them. So the 0 matrix, the one with all zeros, is the one that is the analog of 0 when it comes to matrices. The question then becomes, is there a matrix which has the properties of the number 1, that any matrix times itself is equal to the original matrix? And the answer is yes, and there's infinitely many of them. They're all square matrices, and they look like the following. I sub n, it's called the multiplicative identity matrix, the multiplicative identity matrix of order n by n. It's got to be square. Of order n by n is the matrix that has 1s along the main diagonal, top left to bottom right, and 0s everywhere else. This is the multiplicative identity matrix, and it has the property that A times the identity on either side is equal to itself. Now, we normally don't include the subscript on I, because remember, there's infinitely many of them, one for each n. So when we say capital I for the identity, it's assumed to be the one that fits the problem. Just like the 0 matrix above is the one that fits the problem, so also here, it's the identity matrix that fits the problem. We don't tend to write the n unless the problem is stressing something in regards to the size. So the identity matrix, these are the ones for which you get back the same thing. Notice that it's not ones all over the place. That does not work. It's ones along the main diagonal and zeros everywhere else. So with that under our belt, let's go ahead and jump now into exercise 9B. And as always, for every one of these exercises, you should be trying them yourself before you see the solution for maximum benefit. So question number 1 for exercise 9B. First, it lists 6 matrices. 1, -2, 2, 3, 2 by 2 matrix. B is a 2 by 3, 2, -4, 1, -1, 0, 3. C is a 3 by 2, 1, 0, -1, 2, -2, 3. D is a 3 by 3, 1, -2, -1, 3, 0, -4, -3, 2, 1. E is a 3 by 1, 2, 1, -3. And F is a 3 by 2, -3, -1, 2, 4, 5, -2. And the question reads, find each of the following matrices if possible. And if it is not possible, state the reason. So A, C plus F, A. Notice that A is being multiplied on the right. So order of operations still holds. Parentheses are their purpose in life, or at least their purpose in math, is to tell you do this first. Otherwise, it would be FA and C plus that. But no, C plus F, do that first. Am I allowed to? Sure, C and F are the same dimensions. So C plus F is also 3 by 2. So 1 plus -3 is -2, 0 plus -1, -1 plus 2, 2 plus 4, -2 plus 5, and 3 plus -2. There's CF, and then we have A, which is 1, -2, 2, 3. So what do we have here? We have a 3 by 2 and a 2 by 2. The numbers in the middle match. Awesome. And that tells us that we're going to end up with a 3-row, 2-column matrix. First row, first column, -2, -2, -4. -2, -2 is 4, 4 minus 3, 1. 1 and 12, 13. -2 and 18, 16. 3 and 2 is 5. And -6 and 3, -3. Did it fast. Hopefully I did it right. Part B. DE. Well, let's take a look. D is 3 by 3. E is 3 by 1. Numbers on the inside match, so I'm allowed to do it. And so let's go ahead and do it. So I'm going to copy DED. I'm going to duplicate it and bring it down here. Actually, I don't need that part. So there's D. And then E, I'll just rewrite. It's small, 2, 1, -3. And I know I'm going to get a 3 by 1 at the end. So first row, first column. First row only column. 2 minus 2, 3. 6, 0, 12. And -6 and 2 is -4, -3, -7. Okay, C. ABC. Ooh, ABC. So A is 2 by 2. And B is 2 by 3. And C is 3 by 2. So remember, with ABC, with 3 matrices, assuming that you're allowed to multiply, you can do them in either order. So you can do, not either order, sorry. You can do either the first 2 and then the third, or the second 2 and then the first. In this case, let's do the first 2. When I do the first 2, I'm allowed to do it, and I end up with a 2 by 3. And when I get that result, the 2 by 3, the 3 and the 3 match, and my overall result is a 2 by 2. But let's get some practice with your calculator mode. So what I'm going to do is I'm going to go to my calculator and I'm going to go second matrix, edit the first matrix. It's 2 by 2 again. 1, -2, not -2, but -2, 2 and 3. Okay, quit out, matrix, go down to B. Sorry, go to edit, and then B, this is a 2 by 3. 2, -4, 1, -1, 0, 3. Quit out, matrix, edit, go down to C. This one is a 3 by 2. 1, 0, -1, 2, -2, 3. Quit out, back to matrix, enter A, back to matrix, enter B, back to matrix, enter C, hit overall enter, 18, -23, -13, 17. D, CF. C is 3 by 2. F is also 3 by 2. Uh-oh. Nope. Can't do it. And then we have E, which is 2A, the number 2 times A minus 3 times the 2 by 2 identity matrix. Okay, well, scalar multiplication is always defined. 2 times A is just a number 2 times A. How do I multiply a number by a matrix? Each entry gets multiplied by that matrix. So if I look up at A, 2, -4, 4, 6, minus 3 times the 2 by 2 identity matrix. Well, the identity matrix is 1, 1 with zeros there because zeros everywhere else. And then I multiply each entry by 3. That just gives me 3, 0, 0, 3. They're both 2 by 2, 2 minus 3, -4 minus 0, 4 minus 0, 6 minus 3, and I'm done. So hopefully you got that all correct. And let's move on to question number 2. P is 4 by M. Q is 2 by N. And PQ is 4 by 3. What is M and what is N? So as always, pause, solve, check. So P is 4 by M, Q is 2 by N. These two have to match, and we end up with those. Only way M and 2 can match is if M is equal to 2, and if 4 by N is what we end up with, then we know we end up with a 4 by 3, N must be equal to 3, done. Question number 3. Find the matrix that has the effect of summing the entries in every row of a 3 by 3 matrix. That is, if A is equal to A, B, C, D, E, F, G, H, I, a 3 by 3 matrix with arbitrary numbers, we want to find a matrix AB such that the first row of AB to 3 by 1 matrix is A plus B plus C, just adding the entries. Then we get D plus E plus F. Then we get G plus H plus I. This is the goal. So just conceptually, A is 3 by 3. B is unknown currently, but we know that AB overall, the product AB is 3 by 1. So B must be, this is for you to fill in, that has to be a 3, so those match, and that has to be a 1. So B must be a 3 by 1 matrix. B is 3 rows, 1 column. Currently, we don't know what it is. X, Y, Z. It's unknown. X, Y, Z. What is it? Well, what I do know is that if I multiply A times B, which is A, B, C, D, E, F, G, H, I, times the currently unknown X, Y, Z, I get A plus B plus C, D plus E plus F, G plus H plus I. Now, we will later learn techniques for solving this, but we haven't learned them yet. So there has to be a trick. And it's not really a trick so much as an observation. We want A times X, B times Y, and C times Z added together to give us A plus B plus C. Well, I just notice that if X and Y and Z are all 1, that works. And that will work for the second row. And that'll work for the third row. So B is just the matrix 1, 1, 1. I just noticed that that works. They're not going to ask a question until we develop some more matrix multiplication and matrix properties, how to solve more general situations. Right now, it's just basic. 1, 1, 1 works. Let's move on. Question 4. Consider the matrix A equals, this is a 2 by 3, 3, negative 2, 1, negative 1, 5, negative 6. And it says find the matrix B. This is part A. Find the matrix B. We want AB to equal to A. In other words, we want B to have the identity matrix properties, because we know the identity matrix is the one that gives us what we started with. Well, A is 2 by 3, and we end up with 2 by 3. So the only way that can work is if B is 3 by 3. So that these numbers match, I'm allowed to multiply, and I end up with the appropriate dimensions. So what is B? B is the 3 by 3 identity matrix. Part B, it says find the matrix C such that CA is equal to A. Now C is on the other side. Well, again, A is 2 by 3. We want to end up with a 2 by 3. And the only way that that can happen is if C is, drum roll please, 2 by 2. So that those match, and then those give us what we want, which means C is the 2 by 2 identity matrix. So C, why does A not have a multiplicative identity? Why is there not a matrix which you can multiply on either side of A and get what you started with? And the answer is because it's a different matrix. I2 and I3 are different matrices. One is order 2, one has order 3, 2 by 2 and 3 by 3. They are different. They might look the same, they might have similar properties, they might have similar characteristics, but they are not the same. I2 is not equal to I3. So there is not a single matrix. If you go back above to our definition here, right? This right here, it's got to be in both directions. It can't be two different matrices, one for one direction, one for the other direction. In this case, there's no multiplicative identity because there's no single matrix that works for both directions. Question number, well, that's not straight at all. Question number 5. Reads as follows. And this is the last question in section 9b, and it's a little lengthy, a little wordy. It says, a manufacturer makes 3 types of products. So there's product 1, product 2, product 3. And each of its 4 plant locations, location 1, location 2, location 3, location 4. Matrix A, which they give below, let me first write it out. It's a 3 by 3 matrix, 20, 35, 15, 18, 28, 12, 45, 72, 32. Matrix A gives the daily amount in kilograms of carbon monoxide, sulfur dioxide, and nitric oxide produced during the manufacturing process of each product. So there's 3 columns, one for carbon monoxide, one for sulfur dioxide, one for nitric oxide, and then there's 3 rows. So those 3 rows must be referring to the products, one for each product. Oops, P1, P2, and P3, because it can't be locations. There's not enough rows to correspond to the locations. And it even says, during the manufacturing process of each product. New federal laws require that the manufacturer reduce its daily emissions of carbon monoxide, sulfur dioxide, and nitric oxide by 60%. So the carbon monoxide must go down by 60%. The sulfur dioxide must go down by 20%, and the nitric oxide must go down by 40% from its current value. So the manufacturer takes corrective measures to reduce emissions to meet the minimum daily standards. Okay, very nice of him. Part A, or her. Let matrix N be a matrix whose entries are the total daily number of kilograms of pollutants released for each product after the corrective measures. The total daily number of kilograms of pollutants for each product. Doesn't care if it's carbon monoxide, sulfur dioxide, or nitric oxide. It just wants for each product after the corrective measures. And write down the matrix R such that N is equal to AR, and then find N. So 20, 35, 15, 18, 28, 12. Of course, you should be doing this yourself. First, we want to find R. Write down the matrix R such that N is equal to AR, and then find N. So what is N? N is the total number for each product. That's one number for each product. So N is going to be a 3x1 matrix because it wants one number for product 1, one number for product 2, one number for product 3. The only way that can work is if R is a 3x1 matrix. Now, what are those numbers going to be? Well, the carbon monoxide was dropped by 60%. So how much of the original amount do I want? I want 40%. Drop it by 60%, 40% is left, 40% of 20, 40% of 18, 40% of 45. Sulfur dioxide dropped by 20%, so 80% is left. And the nitric oxide dropped by 40%, so 60% is left. So the R matrix is 0.4, 0.8, and 0.6. Therefore, what is the N matrix? Well, I'm too lazy to do it by hand, so let's go to my calculator. Too many decimals. Second matrix, edit, A, 3x3, 20, 35, 15, 18, 28, 12, 45, 72, 32. Done, quit out. Second matrix, edit, B, 3x1, 0.4, 0.8, 0.6. Quit out. Matrix, enter A. Matrix, go down, enter B. Bam. We get 45, 36.8, 94.8. Lovely. Now, the daily cost in dollars of removing each kilogram of carbon monoxide, sulfur dioxide, and nitric oxide at each of the 4 plants is given by the cost matrix C. So let's write 3. It's a 3x4 matrix. 10, 8, 12, 8, 3, 2, 4, 3, 7, 9, 6, 11. This is the carbon monoxide row, the sulfur dioxide row, the nitric oxide row, and because there's 4 columns, they must be corresponding to the 4 locations. Notice how, again, like the previous problem with adults, children, the males and females, we had one matrix have the carbon monoxide, sulfur dioxide, and nitric oxide as columns, and the other one as rows, so that matrix multiplication could give us something sensible. So it says the daily cost is given by this matrix. Part B, find AC and describe the meaning of its entries. Well, let's first find AC. Again, A is 3x3, C is 3x4. I don't want to do this by hands. Back to the calculator. Matrix, edit, A, 3x3. Oh, I already have it in there. Even wonderful. Okay, go directly to B. Edit, B is 3x4, 10, 8. Oops, I wrote 1. 10, 8, 12, 8, 3, 2, 4, 3, 7, 9, 6, 11. Quit out. Matrix, A, matrix, B, multiply. 410, 365, 470, 430, 348, 308, 400, 360, 890, 792, 1020, and 928. What is the meaning of each of these entries? So what is the ij entry of AC physically meaning? The ith row entry of AC comes from the ith row of A, which corresponds to the ith plant, and the jth column of C comes from the jth location. Product I, location J. That should be an A, not a P. Matrix A. The ith row of A is product I, and the jth column of C is location J. So it is the cost or total cost of removing the pollutants, or is it removing or reducing? Yeah, removing the pollutants from product I at location J. It is physically what the ij entry of AC is representing. And that takes us to the end of exercise 9b. Now, just like once we define matrix multiplication, we want to define what it means to take a matrix to a power. What is a to the k? Well, just like, of course, we're here, k has to be a positive whole number, because we're not ready to define fractional powers and negative powers. We will later, some, well, a little bit, but for the most part, we're keeping it simple. So a to the k is just a times a times a, k times. Of course, this is only defined if a is square. Otherwise, the, m by n, these have to match. The only way they can match is if m is equal to n. So we only define matrix powers if the matrices are square. And how do we determine it? So, oh, it's easy. Just multiply them out. Okay, in fact, your calculator can do that wonderfully, because if you just put a matrix into your calculator to the 10th power and just either multiply it 10 times or just take it to the 10th power, and bam, you have your answer. There's really no shortcut for this, unless if A is diagonal. What does diagonal mean? Something like this. This is the 2 by 2 example, or something like this. This is the 3 by 3 example. Basically, entries along the main diagonal, but zeros off the main diagonal. We call it a diagonal matrix. Then a to the k is simple. It's equal to either a to the k, b to the k, or a to the k, b to the k, c to the k. So basically, you just take each entry to that power, and it's essentially like regular powers. But if it's not a diagonal matrix, just be aware the matrix that you can get at the end could really be just anything. It's there's no rhyme or reason for what you might get. You just got to do the math. So this takes us to exercise 9C. And time-wise, we're good. Okay, exercise 9C. So question 1. A is a 2 by 3 matrix, -1, 2, 4, 3, 1, 0. And B is a 2 by 2 matrix, 3, -2, -1, 1. It says find each of these as possible. If not possible, explain why. So for A, it says find me AB. Well, let's take a look. A is 2 by 3, B is 2 by 2. Uh-oh. No, thank you. Not defined. That was quick. Quick and painless. B, find me BA. Well, A is 2 by 2, I'm sorry, B is 2 by 2, A is 2 by 3. Oh, this does work. So let's do it. 3, negative 2, negative 1, 1 times negative 1, 2, 4, 3, 1, 0. We're going to get a 2 by 3 matrix at the end. This one's small enough that we should do by hand. Remember, we want practice with both. First row, first column. Again, do it by yourself. Negative 3, negative 6, negative 9. 6, negative 2 is 4, 12 and 0, 1 and 3, negative 2 and 1, and negative 4 and 0. Okay, so I get that. C, A squared, not defined. You cannot square or take to a power any matrix that isn't itself square. But D, B squared, that one I can do. But notice that this is not a diagonal matrix, which means I just got to do the math. Of course, 2 by 2, 2 by 2, you're going to end with the 2 by 2. You should always be doing these yourself. 9 and 2 is 11. Negative 6, negative 2 is negative 8. Negative 3, negative 1 is negative 4. 2 and 1 is 3. Okay, so notice that the matrix that we get, 11, 8, 4, 3, these numbers, what do they got to do with the original? Nothing. Now, it says use the following matrices to answer questions 2 through 6. Okay, so these ones, there's a bunch together. And apparently these are all going to be used. So let's write R. R is 0, negative 1, 3, 7, negative 5, and 4. S is 3 by 3, 3, negative 2, 1, 4, 1, negative 3, negative 7, 5, and 2. T is 2 by 2, 1, 2, negative 1, 3. U is 4, negative 3, negative 2, 5, negative 4, 2, 0, 1, negative 1. W is 2 by 3, 1, negative 2, 3, and 3, 2, 1, or negative 1. And X is 7, negative 2, negative 6, and 4. So calculate each of these as possible. These are all for 2 through 6. So those 6 matrices are going to be used for a bunch of problems. Okay, so 2, SR. Can I do it? Let's see. This is part A. Again, always be doing this yourself. I keep stressing this, I keep repeating it, but easy to just to forget. S is 3 by 3. R is 3 by 2, so I can. Second matrix, edit A, 3 by 3. S, we have 3, negative 2. In fact, you know what? I'm going to put all, you know what? Hold on, I'm starting again. I'm going to put all 6 matrices into my calculator. So second matrix, edit. The first matrix is 3 by 2, 0, negative 1, 3, 7, negative 5, 4. So in my calculator, R is my A matrix in my calculator. Next one, edit B. That's going to be 3 by 3. So S corresponds to my B matrix. So I'm going to pause while I do this so I don't waste time, and then just be right back. Actually, I changed my mind because you're doing it, I'm doing it, we're all doing it. Let's do it together. So B is 3 by 3. That's 3, negative 2, 1, 4, 1, negative 3, negative 7, 5, and 2. That's S is my B matrix. Let's go down to edit a third matrix, C, which is going to be my T. So T is going to correspond to C. That's 2 by 2, 1, 2, negative 1, and 3. Quit out. Go edit down to D. That's going to be my U matrix. This is going to be a 3 by 3, 4, negative 3, negative 2, 5, negative 4, 2, 0, 1, negative 1. Quit out, matrix, edit, go down to E. That's going to be my W matrix. That's going to be a 2 by 3, 1, negative 2, 3, 3, 2, negative 1. Quit out, matrix, edit, down to F. That's X is going to correspond to F. That's going to be a 2 by 2 matrix. 7, negative 2. Oh, I hit something wrong. Edit F, 2 by 2, 7, negative 2, negative 6, 4. and quit out. Okay, so now I have them all done. So A, it wants SR. That's B times A, second matrix. B, second matrix. A, this gives me negative 11, negative 13, 18, negative 9, 5, and 50. B, it wants TR. T is 2 by 2, R is 3 by 2. No can do, not defined. C, WR plus X. W is 2 by 3, R is 3 by 2. So when I combine them together, I get a 2 by 2, which is the same as X. And I'm allowed to add a 2 by 2 and a 2 by 2. So second matrix, WR. W is E. R is A plus X is F. So I get negative 14, negative 5, 5, 11. D, W parentheses S minus U. Well, S and U are both 3 by 3s. So when I subtract them, I get a 3 by 3. And W is 2 by 3. Yep, I can do it. So W is E, parentheses, S is B, minus, U is D. Uh-oh. B minus D, did I do it right? S and U. Did I do this wrong? 2 by 3. Let's do it one step at a time. Let's first do B minus D. B minus D. Okay, that gave me a nice thing. And then E times answer. Oh, it worked that way. Strange it didn't work the other way, but maybe the calculators can't do too much at once. And then E is S minus U, W. Well, I already know S minus U is 3 by 3, W is 2 by 3, so this is not defined. Can't do it. All right, that was question 1. Question number 2. Oh, sorry, that was question 2. Question number 3 now. It says, use the properties of matrices to show that you are, so wants to show, we're going to pretend we don't know this, wants to show, the goal is to show that U R plus R is equal to U plus I R. So we want to show this is true. Now, we don't want to actually do the math, but then it says verify your answer. Verifying your answer means do the math, but we want to do it first via the properties of multiplication. So we want to turn one of these into the other. And I think it's easier to start with the right side. U plus I times R. I know the distributive law holds. So I get UR plus IR. And the multiplicative identity says anything times I gives me the same matrix back. So hey, they're equal. And I'm done. It was that simple. And of course, now let's actually verify it by calculating UR plus R on the left. Well, U is D and R is A. So DA, D times A, and then adding to it A again. Okay, so this one, UR plus R is 1, negative 34, negative 19, negative 18, 3, 7. And this one, U plus I, U is a 3 by 3 matrix, so that I is also a 3 by 3 matrix. So I'm going to define a new matrix G as my 3 by 3 identity matrix. So I'm putting in a new matrix, and my calculator G is I3, 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, and quit out. So now we're going to do U, which is D plus G get that, and then multiply that by R, which is A. And I also get 1, -34, -918, and 37. So this is equal to that as well. So not only did I prove it mathematically, but I also verified it computationally. Question number 4. It says in algebra, dealing with numbers, we know that a plus b times a minus b. If you FOIL this out, you get a squared minus b squared, a difference of squares, one of the special factorization formulas. We also know that a plus b times a plus b is equal to a squared plus 2ab plus b squared. Either you can FOIL that out, or you can Pascal's triangle it, if you happen to know that. So that's with matrices, that's with numbers. However, t plus x and t minus x, and t plus x times t plus x are not equal to t squared minus x squared is not equal to t squared plus 2tx plus x squared. And it says expand them using properties of matrices and explain why. So let's go through them. The first one, t plus x times t plus x. Well, I can distribute. I can consider the first entry here as one object A. So I get at plus ax, where A is t plus x. And then I can distribute again. I get tt, or t squared, plus xt plus tx plus x squared. And here's the key. Xt and tx are not necessarily equal. So we do not get 2tx. Looks like I was doing the wrong one. I did this one first. Okay, so we do not get 2tx because xt and tx are not necessarily the same. If I now do the other one, t plus x, t minus x, again, I'm going to call this first piece here A. So I get A, so I get A times t minus x. Sorry, yeah, A times t minus x plus, sorry. So distributing, I get at minus ax, a is on the left. That's t plus x, t minus t plus x, x. And now if I distribute again, I get t squared plus xt minus tx minus x squared. And again, these two guys do not necessarily cancel because they're not necessarily equal. Therefore, we don't get t squared minus x squared. Okay, so that was it. Question number 5. Show that SU squared is not equal to S squared U squared, even though that's something that is true with numbers. Why is it not true here? Well, let's first do it with properties. SU squared is SU times SU, which is just that, SU, SU. Whereas S squared U squared is SSUU. And SU, the inner two, these are not necessarily equal to each other. So we don't necessarily get the same thing. This is all stems from the non-commutativity of matrix multiplication. What is SU squared? Well, let's go back to our calculator. S was B and U is D. So second matrix, B times second matrix, D, get that, and square it. Gives me 37, negative 33, negative 264, negative 348, 352, negative 240, negative 9, 508. Meanwhile, we want S squared, U squared. So again, I think S was, they were B and D, right? Yes, S is B and U is D. So this is basically B squared, D squared. Second matrix, B squared. Second matrix, D squared. Now take what I got for B squared and multiply it what I got for D. Oh, it won't let me do it. Why not? Oh, I thought I hit the wrong button. B squared times, and it won't let me put it in. It won't let me put it in. So second matrix, B, second matrix again, B, second matrix again, D, second matrix again, D, I just did it manually like this, B, B, D, D, B squared, D squared, and this gives me 49, negative 52. I don't even have to keep going. I already see the first entries are not the same, so I know they're not equal, but just for completeness, I get a completely different matrix, not even close. I mean, they got nothing to do with each other. So they are not equal. Matrix multiplication, not commutative. All the properties, all the results that are consequences of that still hold. Question 6. Show that 2RT equals 2RT equals R2T. In other words, when it comes to scalar multiplication, the scalar can go in front, can go with the first, can go with the second. I don't care where you put it. Scalars can go wherever they want. So we'll show this. Okay, well, let's go R and T. R was A and T is C. Okay, so we're dealing with A and C here. So 2 times matrix A times matrix C. This gives me 2, negative 6, negative 8, 54, negative 18, and 4. Next, 2 times A, that's 2R, times matrix C, oh, same thing, and matrix A times, well, let's do it this way, 2 times matrix C, and then matrix A times that. Oh, your calculator won't let me do it. 2 times parentheses, let's see if this works, 2 times matrix C and parentheses, yep, that works too, okay. The matrix, I mean, the calculators are a little finicky. Sometimes it allows things, sometimes not. Have to play around with it more to see exactly what you can do and what you can't do. But worst case scenario, you can always write it out by hand. That's always a possibility. Question 7. Consider the matrices. A is 2 by 2. It's negative 3, 5, 1, negative 2. And B is 2 by 2, negative 2, negative 5, negative 1, negative 3. We want to show A that AB is equal to BA. Interesting. This is one of those examples where you get the same thing in both directions. So the second matrix, we can do it by hand, it's 2 by 2s. So AB is negative 3, 5, 1, negative 2. B is negative 2, negative 5, negative 1, negative 3. So 6 minus 5 and 15 minus 15 and negative 2 plus 2 and a negative 5 plus, oh, look at that. We get I2. We get the 2 by 2 identity matrix. Crazy. And BA, which is negative 2, negative 5, negative 1, negative 3, negative 3, 5, 1, negative 2. And we get 6 minus 5, we get negative 10 plus 10, we get 3 minus 3, and we get negative 5. Oh, look at that, we get I2 again. So in this case, we've shown not only is AB equal to BA, they're both equal to the 2 by 2 identity matrix. Now, you might be looking at these two matrices A and B and saying, well, a lot of those numbers are very similar, 3, 5, 1, 2, different arrangements, negatives, positives. There is certainly a connection between them, and we are going to get more into that later. There's no question about it. And then part B, it says, what is 2AB to the 10th power? Now, I don't want to do 2AB, 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 and so on. I want to use some properties. So first of all, I mean, conceptually, I know this is 2AB times 2AB all the way to another 2AB at the end. And those 2's, those are scalars. I can move them all to the front. That's 2 to the 10th power. But each AB is the identity matrix. So it's I2 times another I2 times another I2. Well, 2 to the 10 is 1024. And I2 has the property that anything times itself equals to that. So I2 times I2 all the way to the end is just I2. You don't lose the matrix. You can't just say, oh, it's equal to 1, and therefore the answer is 1024. You can't take a matrix to a power and get a scalar. You have to get a matrix back, and it has to be the same size. So it's going to be 1024 times the 2 by 2 identity matrix, which is 1024, 0, 0, 1024. And then finally, we have number 8, last question of the section. Michael makes the following conjectures for all square matrices. Michael says, I believe that AB to the n is equal to A to the n, B to the n. And I believe that a scalar A to the n equals the scalar to the n, A to the n. If you agree with Michael's claims, prove them. And if you disagree, write counterexamples. So first, as always, pause and think about it. So I agree with this one. I'm happy with this choice because scalars I can move to the front, but we've already established, I don't got to do this again. We've already established that this is not correct. We already showed earlier that right here, for example, number 5, SU squared is not equal to S squared U squared. That's my counterexample. You want a counterexample for this one? Counterexample. Exercise 5. That's my counterexample. I already know that's not true. This one, however, is true. Ka to the n, that's just Ka times itself, n times. All the scalars come to the front, leaving me with all the matrices at the end. We like that one. So that takes us to the end of section 9.2. We now know how to add, subtract, and multiply matrices. We know some of the properties of matrices, like the non-commutativity or the associativity or the distributivity, and some of the consequences of non-commutativity that we might think would be true. But we haven't really used matrices to do anything yet. We've seen some problems like with the power plants and the carbs and the protein fat example. And we've seen some examples where you can use matrices to kind of summarize data and look at it in a very structured way, but we haven't really used matrices for anything. That's going to start in section 9.3. So I will see you there. Bye.